Okay, thank you very much. Yeah, indeed. Spectral characterizations of distance regularity of graphs. That's what I will talk about. This is, well, I will talk about this topic first, giving an overview of older results, and then later I will focus a little bit more on the recent results. This talk that I will give is embedded in this more general problem here, that if you have any graph and you, well, you can get the spectrum of that graph, but the question is, of course, can you go back, right? Does the spectrum of a graph, and by that I mean the 0-1 adjacency matrix in this case, and can you go back to determine the graph completely? And in general, of course, that question is no. But yeah, here's a bet that Willem Hamers and I made more than 10 years ago already, that almost all graphs are determined by the spectrum. At that time, there was a little bit of computational evidence that supported that bet. Nowadays, well, Willem would conjecture that this is true. And nowadays there is some theoretical evidence also, results by Wei Wang, that support this conjecture or bet, if you want. Okay, but I will talk about, I will focus on distance regular graphs. And actually, if you restrict to distance regular graphs, then the question is completely different than the general problem. But first, okay, what's distance regular? What does it mean? So Peter already explained it a little bit. If you look at the layers, if you fix a vertex, look at the layers of graphs that are at a certain distance, then between those layers, the graph behaves very irregular, right? So every vertex at layer I has the same number of vertices at layer I minus 1 as any other vertex in that layer. Yeah, so these are constants, Ci, Ai, and Bi. Right, and these numbers are the same for whatever vertex you fix. Yeah. Okay. So that's a distance regular graph. Strongly irregular graphs, also already mentioned by Peter, are distance regular graphs, and here are some other ones: Hamming graphs, Johnson graphs, Grassmann graphs, odd graphs, and they will come back later in this talk too. Famous families of graphs. Now, the bet or the conjecture that almost all graphs are determined by the spectrum is not true for distance regular graphs. Results by Dima van der Vlas, they imply that almost all distance regular graphs are not determined by the graphs. Right? Dima constructed so many strongly irregular graphs and distance regular graphs with diameter 3 with the same spectrum, with the same parameters, yeah, that you can draw this conclusion. Okay, now so let's translate this property of distance regular graphs into several other properties. So if you look at the distance, the adjacency matrices, the distance I adjacency matrices, then you get this 3-term recurrence. Right? If you multiply the adjacency matrix A with AI, then you get that equation there, and it implies that AI is a polynomial of degree I in A. Yeah, and that holds for all I up to the diameter. Yeah. Now, what's important in what I will tell later on is this characterization by Peter Rowlandson, which determines distance regularity in terms of walks in the graph. Yeah, so the number of walks of a given length from a given vertex to another given vertex, yeah, that's only depending on the length of this walk and the distance between x and y. Yeah? That's a characterization of distance regularity. Okay, now I'm talking about intersection numbers, but I started with eigenvalues, yeah, and these are not the same, of course, but they are related in case you have a distance regular graph. In case you have a distance regular regular graph, then the eigenvalues follow from the intersection numbers and vice versa. Yeah? And we know that the intersection numbers do not determine the graph in general. That's, for example, what Dima van der Vla showed. But there are more basic examples, I guess. Yeah? So that means, well, that also the eigenvalues do not determine the graph in general. Yeah, that's for a distance-regular graph. Yeah? Okay, but more generally, you can ask, okay, can you conclude from a given set of eigenvalues from a spectrum whether the graph is distance-regular? Yeah, that's a different question. Right, so you don't assume distance regularity. If you assume distance regularity, then intersection numbers and eigenvalues correspond. Okay. Now I was mentioning this characterization of Peter Ronenson in terms of walks in a graph. Now the spectrum, so the eigenvalues of the graph, they can be translated into properties about the closed walks in a graph. So a closed walk is a walk from a vertex to itself. Yeah, the characterization by Ronenson was about walks from a vertex x to a vertex y at any given distance. Yeah, but here we talk about closed walks, walks from a vertex to itself. Right? And so you can actually translate all the spectral properties into properties about the numbers of closed walks in a graph of a given length. Yeah, so actually, if you have information about these the numbers of these closed walks, then you know the spectrum and the other way around. Yeah, so all this information, that's what I'm trying to say here, all spectral information is in these closed walks. Yeah, but we would like to know things about any kinds of walks. Yeah. Okay. Now here are some generalities that some combinatorial properties that follow from the spectrum. Yeah. So if you have a graph and you know the spectrum, then you also know the number of vertices, you know the number of edges, you know the number of triangles. This all follows easily. As I said, the number of closed walks of given length. Moreover, you can see whether a graph is bipartite, whether it's regular, well, etc., etc. The bottom two are about the girth and odd girth, and that will come back later because if the girth or the odd girth is quite large, relatively large, then we can say more about distance regularity from the spectrum. That's why I'm mentioning it here. You can also get other properties from the spectrum, of course, but I'm just mentioning these here. Okay, so now distance regularity is not determined by the spectrum. So the property of being distance regular you cannot see from the eigenvalues in general. And here is one example. This is a graph which has the same set of eigenvalues, the same spectrum as the Desargues graph, the double Petersen graph. Yeah, so it's this nice graph. Yeah, and you can check it's not distance regular. Yeah, and it's actually a quite old result. It was discovered in the 70s of the previous century. That this has the same eigenvalues as the Desargues graph. Okay, so now the question is, okay, so in general you cannot decide whether you cannot decide for sure whether a graph is distance regular from the spectrum, but in some cases you can see this, and that's more or less in this what I would now call a classical result. Yeah, so if you have a distance regular graph, yeah, with the diameter d, valency k, girth g, yeah, then if you have a different graph with the same, or a potentially different graph with the same eigenvalues, yeah, then you know it is also distance regular if one of these properties holds. Yeah, so and these properties are spectral properties. Yeah? Even though, okay, the first one, the girth is at least 2d minus 1. That looks like a combinatorial property, but it is, you can actually express that in terms of the eigenvalues. You can see that from the eigenvalues. Yeah? Okay, so these I would call classical results. Well, maybe the ones from the previous century are classical, and the others are just old, I would say. Yeah. So the first one is, I guess, by Anders Brouwer and Willem Hamers about the girth that I just mentioned. Yeah. So here the restriction is that you need a distance regular graph, yeah, and you have information about another graph with the same eigenvalues as that distance regular graph. And what I would like to do later on in this talk is generalize this. So I want to get rid of the assumption that you have some distance regular graph, yeah, and a graph co-spectral to that distance regular graph. I just want to have a graph and a spectrum, and then say something about distance regularity. Yeah? So that's what I will do later on. Okay, but yeah. So I also mentioned four or five graphs which are determined by the spectrum. But here's also a very important family, the Johnson graphs, and these are not determined by the spectrum, right? So there are co-spectral graphs, so graphs with the same spectrum as the Johnson graphs, yeah, that are not distance regular. Yeah, so this is in contrast to, for example, the Hamming graph H3Q for Q large enough, yeah, which has that property. Yeah, so different families of graphs behave quite differently. Okay, before I continue, I would like to draw your attention to a survey of that we are currently writing. We is Jack Colin, Hajime Tanaka, and myself. We're working on a survey of distance regular graphs, and we're almost finishing it. You can find a draft, unfinished manuscript on my website. So if you're interested in that, please have a look. And if you find anything important missing or incorrect, then let us know. That would be very helpful to us. Okay, so what I was saying, I wanted to generalize this classical result. What do I need for that? I need to think about certain polynomials. So, given if you have the spectrum of a graph, you can get polynomials that resemble the distance polynomials of a distance regular graph. So these distance polynomials are the polynomials pi such that ai is pi of a, yeah, in case of a distance regular graph. So I want to get these polynomials for any graph, yeah, no matter whether they're distance regular or not. And I can construct these from this inner product that I can define for any spectrum, yeah, by considering an orthogonal system of polynomials with respect to this inner product that I define. Yeah. And so from this orthogonal system you get this three-term recurrence, and this is very much related to the equation that I showed you before for the distance regular graphs. Yeah, but in this case I don't know if these betas, alphas, and gammas have any combinatorial meaning. Yeah, they're just, you find them from the spectrum. Yeah? But in case you have a distance regular graph, then these betas are the B's, and the alphas are the A's, and the gammas are the C's, exactly. Yeah? So in case the graph is distance regular, they're exactly what they should be. Okay. Now here is Another very important and classical result, the spectral excess theorem. So with these polynomials, you can actually get a bound for the number of vertices that are at extremal distance. So if you fix a vertex and you look at, so the little d here is the number of eigenvalues of the graph -1, and we know that the diameter of a graph is at most this little d. Yeah, so and now if you look at the number of vertices from a fixed vertex at this extremal distance, and you average over all vertices, that's kd bar there, that number is at most pdk, where pd is one of these pre-distance polynomials that I just introduced. Yeah, and you get this inequality, but what's more important is that if you have equality, then you can conclude that the graph is distance regular. So this is a very interesting, a strong characterization of distance regularity. So if you have the spectrum and you count what's at extremal distance, yeah, then you can conclude whether the graph is distance regular or not. Yeah? Okay, so I introduced these predistance polynomials for regular graphs. I started with regular graphs, but recently we showed that if you use the Laplacian matrix, that you don't need to restrict to regular graphs. Yeah, so there's a way to get around from also to non-regular graphs. It's a minor extension of the classical result. Okay, so what do these pre-intersection numbers, these alphas, betas, and gammas, mean? So here's a graph that you probably can't see. It's a very nice graph on 12 vertices of degree 3. Well, it's actually not so important what the graph looks like. What is important is, well, so so in a distance regular graph, yeah, the betas, alphas, and gammas, you have as many as the diameter, yeah. But here you see you have these parameters up to a little d equals 10. Yeah, but the diameter of that thing is 3, I think. So there are, first of all, many of these pre-intersection numbers, yeah, much more than the intersection numbers of a distance regular graph. Yeah. Now you also see that some of these numbers are negative. And of course, intersection numbers in distance regular graphs cannot be negative. Yeah. So these pre-intersection numbers, they behave a bit differently than intersection numbers in general. Yeah. I try to make some of these numbers in green. You probably can't see that either. But what I want to show you is alpha 1 is 0. Yeah? And that has a meaning. The meaning of it being that there are no triangles in this graph. Yeah? And so actually, here's a result, recent result, that characterizes the odd girth. So the length of the shortest odd cycle in the graph. Yeah, you can see that from these alphas. Yeah, so as long as these alphas are 0, yeah, you have no odd cycles. Yeah. And you can also characterize bipartiteness. Okay, and this can actually be used to generalize one of these results that I showed you earlier on, the result by Huang and Liu, that you can characterize generalized odd graphs by the spectrum. And generalized odd graph, those are almost bipartite graphs. You have only odd cycles of the largest length. You have to go up to the diameter, and then you can make a cycle back, an odd cycle back. Yeah, so the intersection numbers A1 up to AD minus 1 are 0. Yeah, and examples of these are the odd graphs and the folded cubes. Here's also, I also mentioned one intersection, intersection numbers of a very interesting but unknown distance regular graphs. So, well, the question is, so this is one of the smallest unknown parameter sets for the distance regular graph. That's a very interesting one, and it's interesting that also you see C2 is 1. So it's an open question whether there's a distance regular graph with that parameter set. I find it a very interesting one. Maybe you can work on it with you later this week. Okay, so Willem Hamers and me, we showed actually, so this extension of the result by Huang and Liu, yeah, that you can characterize a graph with the same spectrum as a generalized odd graph, as a distance regular graph. Yeah, so we actually in this result we don't require that the graph is co-spectral with the distance regular graph, right? So here the result is, so if you have the spectrum and you know the odd girth is as large as possible, then you know it's a distance regular graph. Yeah, generalized odd graph is a distance regular graph. So this is one type of extension of this classical result. Now, it was also extended for non-regular graphs. And recently we extended it a little bit further. So if you have a graph where these alpha i's are non-negative, so that's one small but important constraint, then you have this inequality on the gamma d in terms of the bound in terms of the eigenvalues, and you have equality in this bound if and only if it's a distance regular generalized odd graph. So this strengthens the previous two results here on this slide. Okay, so going from odd girth to girth, we have a similar characterization of the girth in a regular graph. Yeah, so in general, if you know the spectrum of a graph, you cannot see what the girth is. Only if you know that the graph is regular, which you can see, by the way, from the eigenvalues, you can see what the girth is. Yeah? And here we expressed it in terms of properties of these pre-intersection numbers. Yeah, so the alphas are 0, that means that there are no odd cycles, and then the gamma i's being 1 means there are no even cycles. Yeah, it's exactly what you expect. Yeah? I mean, if you know about distance regular graphs, you need these properties on the AI's and the CI's for the graph to have girth that much. Okay, so using this and some other properties, we indeed managed to generalize the results that I mentioned before, yeah, in the sense that we don't need anymore the property that a graph is co-spectral to an actual distance regular graph. Yeah, so we just have these properties in terms of the eigenvalues. Yeah. So any graph that satisfies one of these conditions is distance regular. Okay, before going in the other direction, so now I mentioned a few characterizations of when it is distance regular. So after thanking these people here, I will move in the opposite direction. So yeah, I would like to thank my co-authors on all of this work. Without them, I could not have given this talk, of course. So I would like, you see some of these are here in the audience. Ida is here. She's giving a talk in the afternoon. Jack is also here, is also giving a talk in the afternoon. So Unfortunately, Michelangelo couldn't come. It was already mentioned by Andy. Willem is going to be here later today. Yeah, he promised me that he would be here when we started drinking beer. And the others are not here, so, but thank them anyway. And I would also like to thank Andy and the other organizers of this conference. It looks very promising, the program. Okay, so let's move into a different direction. So I would like to get back to that twisted Desargues graph that I showed you earlier on. The classic example of a graph that has the same eigenvalues as a distance regular graph. So you can actually generalize that. Yeah, in the sense that the Desargues graph is a doubled Petersen graph. Petersen is an odd graph. Yeah, so here is a description of the doubled odd graph. Yeah, so if you fix a set of 2D minus 1 points, yeah, and you look at the partial linear space of D minus 1 sets on this 2D minus 1 set versus the D sets. Yeah, so you have points and lines of a geometry, and you have incidence between these points and lines whenever there's containment. Yeah? Very simple. Yeah, so the point graph and the line graph of this partial linear space are the Johnson graphs, as I wrote them down there. Yeah? And moreover, most importantly, the incidence graph is the doubled odd graph. Yeah, so in terms of what Rosa Mary Bailey was saying, incidence graph is the Levi graph, and the point graph is the concurrence graph. I'm not sure if you also have a term for the line graph. Not yet. Yeah, so that's this is a bit different terminology from the geometry, finite geometry side, I guess. Now, what I will do is I will change this partial linear space in such a way that the point graph will not change. Yeah, and that means that the spectrum of all these objects will not change either. Right? So the spectrum of these three graphs are all related. Yeah, if you know the spectrum of one of them, then you also know the spectrum of the other two. Yeah. So if I can change this partial linear space and keep one of these things the same, then I will have co-spectral graphs for the others. Maybe they will be the same also, that could happen too, but that's, of course, I want to change them in such a way that that will not happen. Yeah? Okay, so what I will do is, in this ground set that I fixed in the beginning, I fix one extra element h, yeah, and as points I keep the same objects, d minus 1 sets, but I'm going to change the lines. Yeah, so instead of the d sets, I will take the d sets that contain this fixed h. That's one part of the lines, and the other lines are the d minus 2 sets that do not contain this h. Yeah. Now you can actually show that the point graph has not changed. Yeah, that's quite easy to do. Now, unfortunately, the line graph also didn't change. It looked like it's going to change, but you can actually show it's isomorphic to what you had to start with. However, the incidence graph does change. Yeah, it's not distance regular. So this incidence graph is not distance regular. Yeah, it's but we know it has the same spectrum as the doubled odd graph, but it is not distance regular, so it cannot be the doubled odd graph either. And we call it the twisted doubled odd graph. Yeah? So we get this thing, and the smallest example where you have to start with the Petersen graph, yeah, you get the twisted Desargues graph that I showed you earlier on. Yeah? Okay, now we showed actually that this is the only non-distance regular co-spectral graph. Yeah, co-spectral with the doubled odd graph. that has as a halved graph this, as a point graph, this Johnson graph. Yeah? So this is the only way you can twist this partial linear space so that it keeps the point graph intact. Yeah? Okay, now instead of sets, you can go to subspaces over a vector space, a 2D minus 1 dimensional vector space over G of Q. Yeah, and you can try to generalize this and do the same thing. So instead of subsets, we talk about subspaces. Yeah, and we can do this, try to do the same trick for the doubled Grassmann graph instead of the doubled odd graph. Yeah, so if you do that, well, you keep as point graph the Grassmann graph with these parameters there. And you get the incidence graph indeed co-spectral to the doubled Grassmann graph, but again, it's not distance regular. It's quite easy to show that that's not happening. It's a twisted doubled Grassmann graph. So we also for the doubled Grassmann graph, we get a graph which is not distance regular, which has the same spectrum. Yeah. Okay. What happened to the line graph here? Well, you can show. Well, it follows it's co-spectral to what you started with, but here the isomorphism that worked in case of the sets doesn't seem to generalize to here. So here something strange is going on, and actually what you get is a distance regular graph. Yeah, so, and you can actually use the spectral excess theorem that I showed you earlier on to show that this graph is distance regular. Yeah, but it's not a very nice graph. This graph is not vertex transitive, so it's not the same as the Grassmann graph. Yeah, so here we have new distance regular graphs that are not vertex transitive, in fact. Yeah, that's what I mean by ugly, not vertex transitive. Okay, so that was a very interesting and unexpected discovery. It's sort of a side product of trying to find co-spectral graphs. Yeah, so, and currently it's this family that we constructed is the only family of distance regular graph with unbounded diameter that's not vertex transitive. Right? There are some families up there, 3 families of graphs that are not distance transitive. Yeah, and in the picture is the smallest Dup graph, also known as the Shrikant graph. But the graphs that we constructed are not even vertex transitive, so they are very ugly. Yeah. Okay, so actually ugly distance regular graphs are very useful. Oh, by the way, here's, I forgot to mention. Yeah, so this also the Grassmann graphs. So in this case we didn't get non-distance regular co-spectral graphs, but in another way you can construct these still. Yes, so you can show that that any Grassmann graph of diameter at least 3 has co-spectral graphs that are not distance regular. Okay, so yeah, so these ugly distance regular graphs and ugly almost distance regular graphs, so also the twisted Desargues graph, you can use them to construct families of co-spectral graphs. So now I'm going back to the problem on the first slide, yeah, where we asked, okay, are all graphs determined by the spectrum? Yeah, so we can use these ugly almost distance regular graphs to produce co-spectral graphs by just adding or adding vertices, removing vertices, adding edges, etc., etc. All sorts of very small operations that you do on the graph. Yeah, and if you take different vertices, so if the graph is not vertex transitive, you take vertices from different orbits, and you do this operation, for example, remove that vertex, and you get co-spectral graphs, which are not isomorphic. Yeah? Right, so for example, these two graphs are co-spectral. Right? I removed one vertex from the twisted Desargues graph, but two different vertices. I get two non-isomorphic graphs with the same eigenvalues. So it's easy to construct co-spectral graphs from these ugly distance-regular graphs, or ugly almost distance-regular graphs. Yeah. And this is one operation, but you can do others as well. Okay, so one final thing is recently we also found that from regular 2 graphs, from very beautiful regular 2 graphs, we can construct co-spectral graphs. So yeah, I wrote it here as Taylor graphs, but I didn't know that Peter was talking about 2 graphs right before me. So we actually worked in the switching classes of regular 2 graphs, in particular of the symplectic regular 2 graphs, right? And by looking at different graphs in this switching class, we construct co-spectral graphs. Yeah, all of that seems to point towards the statement that graphs are not determined by the spectrum. Right? However, these are very special constructions, right? And on the family of all graphs, you need very nice graphs to do all of this. So even these ugly graphs that we constructed are very nice in some sense. Yeah, if you compare them to other graphs, yeah? And they're very rare, right? So we make these co-spectral graphs from very nice graphs, yeah, and luckily they don't contradict the conjecture, the overall conjecture. Okay, so that's all that I wanted to tell. Thank you for your attention.
Thank you very much for your talk. Are there some remarks, questions? So, if this is, yeah, please.
You said that almost all graphs are determined by their spectrum at first?
That's what we think.
That kind of contrasts with this other statement that almost all trees are not determined by their spectrum.
Yeah. Yeah.
Is there something in between for graphs that have a limited number of cut points or something?
Not that I know.
The way the theorem works for trees is based on looking for special types of cut points.
Yeah. Yeah, that could. Yeah, so the proof for trees. Yeah, I'm sure you can generalize that somehow to get other families. But yeah.
Good. Other questions or, yeah? A little bit louder. What are the beautiful distance-regular graphs?
I mean, well, I can mention the classical families. Oh, they're boring. Beautiful and boring. Yeah. Well, I mean, I don't have an offhand definition, but there are many.